Welcome everyone to the Spring 2023 Institute for Data Science seminar series. I'm David Bader, a distinguished professor and director of the Institute for Data Science at the New Jersey Institute of Technology. I'm very pleased to introduce today's speaker, Sutanay Choudhury at the Pacific Northwest National Laboratory. Dr. Sutanay Choudhury is a chief data scientist at the Pacific Northwest National Lab, or PNNL, with over 10 years of experience in artificial intelligence and data science. His current research focuses on development and application of graph representation learning, prediction, and reasoning methods towards solving problems in chemistry, medicine, and the power grid. Dr. Choudhury serves in multiple leadership roles at PNNL, such as the co-director of PNNL's Center for Theoretic and Computational Chemistry, and thrust lead for PNNL's internal initiative on AI research. He has served as PI, co-PI, and contributor on multiple projects funded by the Department of Defense, Department of Homeland Security, Department of Energy, and PNNL's internal research programs, developing multiple systems focusing on graph analytics and graph neural networks. He developed StreamWorks, a streaming graph analytics system that received an R&D 100 award for novel applications in cybersecurity. And today we're very pleased that he'll be presenting his talk on fast and accurate prediction of potential energy functions for 3D molecular structures. Sutanay?
Thanks, David. I really appreciate the opportunity to be present here. David has already gone over my background, and I was going to start by emphasizing that even though I'm talking about applications into chemistry or physical sciences today, all of this probably does not require much background than a high school student in chemistry or physics. I'm a computer scientist by training. I have been working on past 10, 12 years on graph analytics, graph neural networks, and machine learning. One of the things I have really enjoyed over this last decade is working on both, I would say, discrete mathematical approaches that comes from graph algorithms and marrying those to the machine learning or more statistical approaches. And what really comes together is then, because real world problems, they don't really come to you as, most of the time we try to fit our toolboxes to the problems, but if you have the diversity of different techniques, then you can really decide what tools to use for a problem. What I want to talk to you today is, my goal is to convey some of the challenges, what are some exciting problems in physical sciences, in chemistry, that is really, that should be really applicable for those who are working on graph analytics, machine learning, especially like graph neural networks, visualization, those fields, and even language models. So my goal is to make connections or help you to build some bridges for this exciting area of research. I'll try to keep this talk maybe for half an hour, and then want to have an active discussion depending on the questions the audience has. So before jumping into the details, my talk is titled Prediction of Potential Energy Functions. So while I'm going to focus on much broader topics, let's start with the definition of what does energy functions mean and why it's so critical. So these days, as you hear about that, we always are looking for find the next lightweight more materials. We want to design cars that has less weight, consumes less energy. We want to be able to manufacture processes, steel or other things that requires less heat. So these are all the things that collectively contributes to decarbonization. So if you were to think about that, okay, so you probably think about most of the chemical reactions that we think in the factories, that takes a huge amount of extrinsic energy or additional heat. So the reason is that, so if you think about what happens during a chemical reaction, and if you can predict the changes in the energy of the molecules as they go through the reaction process, that's the first step to understanding how much intrinsic or extrinsic energy it requires. So if you think about an input to a reaction, and we can predict the output of the reaction and the energy requirements, the gap between the input and output, that essentially tells you how much heat you need to supply. So as people think about how do we come up with the new materials, being able to estimate those energy gaps or the functions is really, really critical. But that's just one of the applications. So to generalize it, think about that we want to look at atomistic structures. We want to look at chemical systems. We want to represent those, whether you want to represent as matrices, graphs, or some other way. Being able to predict the property of the systems is a first step before we can design new materials, invent newer things. So the basic data structure, as we start talking about this in more detail, is looking at molecular graphs. So many of you, I hope that in this particular in this session, are familiar with graph structures. These are, and a lot of the times we think about graphs, more we think about applications like social networks. So graphs is a mathematical data structure in which you have nodes and you have edges. So which means that you're connecting a set of entities by their different kinds of relationships. So think about Facebook as a great example of a graph. You have nodes that could represent people, could represent images, posts, and so on and so forth. And you have edges that connects these people. And there could be, and there is a semantics with these connections, because I could follow somebody, which is very different from I friend somebody. And you can also have heterogeneous relationships in that the relationship between person to another person versus person posts an image, person likes an image, so on and so forth. So the same analogy also applies to molecular structures. So you can think about the atoms being the nodes in this case, and the different kind of bonds become the edges of these graphs. So the distinction is that now molecular structures also comes with additional properties. They have just as in the social networks, in case of molecular structures, we want to track node-wise properties such as the type of an atom. We may want to track the 3D coordinates, the XYZ coordinates associated with every atom. We may also want to track force fields and other things. So the first step is to recognize that when you think about graph neural networks being applied, so why we think about the machine learning, and it's probably a no-brainer for most of the audience, but the reason is because traditionally predicting the property of molecular system, such as their energy functions or any other properties, like given a drug molecule, you want to know its toxicity. You want to know, will this bind with a specific viral protein? And traditionally, this has been done by high-performance computing or simulations on a supercomputer, because you want really expensive and high precise calculations that take a lot of time. The motivation for bringing in machine learning here is that a lot of the times we can get away with approximations. So you don't have to run simulations that would be consuming 20 massive servers and running over 12 hours. We can get the answer in an instant, provided we have trained these models well. So this is where, if you are representing molecular structures as graphs, then the graph neural networks becomes a natural vehicle for predicting the property of the systems. Now, when you look at graph neural networks, or in academia, most people think about graph neural networks being applied to social networks for recommendations on product graphs, such as Amazon's knowledge graph, and so on and so forth. So it's really important to understand how the setting between a big graph versus the molecular graphs is different. So the first differentiation is that when you're trying to predict, so if you look at something like Open Graph Benchmark, which is today's de facto standard for evaluating the performance of graph neural networks, there are different tasks that focuses on a massive graph, such as one with Microsoft Academic Graph or Wikipedia, and those are a single graph at a billion scale. You will see billions of nodes and perhaps tens of billions of edges, and they are only going to get bigger and bigger. On the other hand, the molecular graphs come from the other end of the spectrum, where you have massive number of small graphs. So you may have millions of small graphs where the number of vertices only range to maybe a few hundreds or to a few thousands. So does it mean that it's easier to train this? The answer is that, well, they come with unique set of challenges. So some of my initial slides are focused on how do you train these molecular graph neural networks efficiently, fast. And then some of my other later on slides are focused on the associated challenges, that if you can predict the properties of the systems accurately, what else can you do? So the first part is that this is where I'm getting into a little bit of the details of the training process. The reason this is because the training these molecular graphs, typically, if you're trying to train a model over a few million samples, it can easily take few days, depending on your compute infrastructure. The problem is that as you know, in machine learning, we never want to train a model just with default parameters, and very rigorous hyperparameter optimization is really critical for getting the best model. So how can we squeeze down the training time of these models to a few hours so that we can experiment by trying different parameters and seeing what's the best predictive performance? So graph neural networks always begins with partitioning a graph over the nodes we have in our cluster. So if you're thinking about doing this on a GPU cluster, we will want to start by partitioning these data sets over different multiple GPUs. The challenge is that if you have a good amount of imbalance in your data structures, so if you have a big molecular database with very diverse amount of diverse molecular structures, so you may have a good number of you may have a lot of molecular structures that are really small, and there might be a good number of them again which are really large. So what happens is that this imbalance in the structure can lead to a very inefficient training process. And this is because most of these neural networks, or graph neural networks especially, require sparse matrix multiplication. So if you are trying to do this sparse matrix multiplications on each of these graphs individually, it's going to be first of all, very inefficient. And number two, it's going to be also be inefficient in terms of a load balancing perspective, that you will be doing processing the small matrices or the small molecular graphs very quickly, and then you'll be waiting for the much bigger graphs to finish the computation. And this is a reality because, so what I'm showing you here on the left side is a sample from one of the largest molecular databases. This is something we have published from PNNL. It's a collection of molecular structures, collection of about 5 million molecular structures. These molecular graphs range from 3 nodes to 25 nodes in size. And what I'm showing on the right is an example of a graph neural network, or 3D neural network, as you like to call it, because we are not just looking at the bonding structures, the graph structure between these atoms or molecules. We're also looking at we're accounting for the coordinates, or the XYZ coordinates, or the geometry to drive the prediction. I'm going to give a very quick overview of what's the intuition behind designing these models, and why graph neural networks is a very good fit for this. So for most of the time, when you're looking at an atomistic system, we think about predicting their properties in terms of many-body interactions. So if you're trying to compute a global property, the property of an entire system, we would like to say, well, let's think about how much influence a single molecule or single atom or a molecule has from its surrounding neighbors. What happens in some of the high fidelity simulations that they try to look at the influence of everybody to everyone. So it's like a many-body interaction. Most of the time, you can live with an approximation where, given a 3D collection of these molecular structures, you impose a radial sphere around every molecule. And then you only consider the molecules that surround a given atom or molecule within that sphere. And then you try to aggregate the properties of the surrounding neighbors on a node, if you call it in a graph. So now if you're constructing a graph in which every node represents an atom or molecule, you are trying to learn its property as a composition over its neighbor's property. And then this is why this is directly maps into how graph neural networks are adept at learning the property of a node as a function of its neighbors. And then if you keep doing this propagation or aggregation of these properties from multiple hops, you can pick up how an atom or molecule behavior could be influenced by something that's far away from it. So what we have is this. So initially, you think about you're learning the property of a molecule or atom as a composition of its immediately surrounding neighbors. And then if you do this propagation process one more time, you're going to get the effect of accumulating information from 2 hops away. And if you do this one more time, you're going to pull in the effect of molecules or atoms that are further and further away. And that is essentially the role of these interaction layers, and which is perfectly captured by a graph neural network. So can you take this kind of a model, and will this just work fine on a GPU? Yes, they will. Now the question is that, can you do better? So in our work, we have been recently exploring the an upcoming emerging architecture called GraphCore. So this is in this case, we are looking at a different class of processors. These are not GPUs, but these are called IPUs. For I mean, the full form of IPUs is, I think, intelligent processing units. But it's just that the design, some of the design principles underlying this architecture is just different from that of GPUs. So in order to simplify what's different about this kind of system, or how you program these systems differently, is that think about that each of this. So I'm showing you here 2 nodes. So each of these dark blue rectangles represents something that's connected to a socket. So each of these, so collectively within every socket that's connected to a CPU, we're going to have 2 processors. So these are contained in these pink boxes. Each of these pink boxes contains about, I think, 1,000 plus cores. So effectively, we have within each processor 1,000 plus cores, each accompanied by a very high amount of cache or local memory. So if we can describe computations, or if we have computations where that fits nicely into these local memories, first of all, so these cores can directly operate on those data structures without making far away memory calls. So our intuition, the reason we started exploring the GraphCore architecture is because our intuition was that for these molecular structures, these are small graphs, these are not really spread over a large memory. Can we take advantage of these local memories and see how they do well? So, and another important property of the architecture is that the high bandwidth interconnect. So if one core wanted to communicate with another core that's on the same socket, they are supported by very high bandwidth interconnect. And this is, I think, becoming an important, it's recognized, the such architecture, being able to improve the speed of communication between cores through dedicated or more hardware interconnects. That's a well-known design principle. And so essentially, we are trying to leverage on this small graphs fitting into getting packed on these local memories that are right next to each of the cores. That's essentially so when it comes to the molecular GNNs, that's effectively what you're trying to accomplish. Now, I mentioned to you before that there was a load balancing problem, that if you do this naively, we will end up, so even if these molecular graphs can be packed onto each of these local memories right next to every core on the processor. So also, for the broader audience, it's important to remember. So all of this is happening. So the graph core, these processors are essentially serving as accelerators. So another major difference with this GPUs with the graph core architecture is that all of this, we're trying to do this when you have a program such as a graph neural network. At the compile time, there is a lot of optimization that's done, and so a lot of things you are upfront. All this computation are getting mapped onto the hardware. So, but still, when you're doing this upfront optimizations, if we are able to map each of these, if we naively map each of these molecular graphs onto a core, that still is not going to solve the load balancing problem. So some of these YOLO cores that are working on a small molecular graph will be done a lot faster than some of the other YOLO cores that are working on a much bigger graph. So the way we solve the problem, and this is a problem that also come up with language models. If you're trying to train a language model on a corpus with sentences that vary widely in size, so some of the transformer architectures, some of the transformer models will process the small sentences faster, and they'll wait for the other sentences that are much longer or paragraphs that are much bigger. So the common trick that's applied here is, can we pack this in an optimal fashion? So think about a bean packing like a problem that we are trying to, given a large collection of inputs, we are trying to sort of divide them into buckets where each of the bucket comes up with a nearly equal amount of workload. So combined with these two optimizations, so first of all, this redistribution of these graphs to optimally fill up each of these processors, that's a platform agnostic optimization. It is not something that's only suited for graph core. It could equally apply to GPUs and any other platforms. So combined with these two optimizations, we have seen some really good performances. So what we see here, I'm not going to get into the details of this, but what we see is that our benchmarking suggests that a graph core processor or graph core system comes up with with about nearly twice speed up over that of today's state-of-the-art NVIDIA GPUs. And I pasted a link to our website in the chat window before starting the talk. And if you go into the website, you'll see our preprint on this work that's already out. So this is sort of the baseline or the story for molecular graphs, why it's important to predict their properties very accurately, and what are the challenges for training machine learning models or highly performant machine learning models. So from here onwards, I want to give you a little bit of a broader overview of now, if you're able to do this, what else can you do? Because this is really in some sense what I've been talking about. Atomistic property prediction is really a kernel or really a core toolbox for designing bigger systems. So first is that transfer learning. So transfer learning is really important because a lot of the times you may think about drug design or any other application spaces. So the chemical structure, so there could be a lot of diversity in the chemical properties. So it rarely happens that you are going to have one universal language, just like an universal language model. We really don't have a universal model for chemistry because each branch of chemistry is quite different from one to another. And so what really becomes important is that, can we train a model, which is the self-speech for transfer learning, that can we pre-train a model and then be able to reuse it on other tasks? So can we reuse this from one database to another? Can we train a model, suppose for just static prediction? When I say static prediction, I mean, given a molecular structure, just give me a property like energy or toxicity or binding with a protein. And now I want to extend it for another task, such as dynamical property prediction. So I want to look at how a drug molecule might be interacting with a protein and how that interaction changes over time. So that's a slightly different task from which I might have trained my initial model, and how do you adapt this? So we have done quite a bit of work on this kind of on this topic, and one of the things we have seen is that you really want to take advantage of different heterogeneous architecture. So what we have done is that we trained a model on a graph core platform, and then we took the same model and applied on a GPU platform. And so this is really, while this sounds simple, there are a lot of complexities in the engineering. There are some standards that have come up on how can we train models that works in a cross-platform fashion. So depending on your interest, that's something that people should check out. And obviously, transfer learning for chemistry or material science applications is only getting started. And I'm going to show why this is a hard challenge in some of my upcoming slides. I'm going to skip the slides a little bit. And so the second half of my talk is that, so let's say you're able to predict the property of a point in chemical space, a molecular structure that represents a point in the chemical space. What else can you do? The reason, as I stated at the beginning of the talk, our bigger goals is coming up with new drugs. We want to be able to come up with lightweight materials. We want to come up with new catalysts that can facilitate reactions that takes less heat. So while getting started while accurate prediction of these atomistic properties is the first step towards doing this, what we are really after is how do we look for new structures that we don't know about? How do you invent new chemical structures that don't exist today? Or given a drug or existing structure, can we change it? Can we re-optimize it for some other property? So if you think about this, so this really comes down to manipulations of the geometric structures. So what I'm showing here on the screen is, so imagine on the right side, the problem comes from more of from a different branch of chemistry. So given a structure, we want to change the structure. We can change the geometry. So means we can play with the symmetry or other properties. And we can also by adding new functional groups, and that would radically affect or influence the properties of the resulting structures. But even if so for someone like me who does not have the very expensive background in chemistry, I think about this as actions in terms of subgraphs. So sometimes if I look at the left example, given a structure which is looking like a hexagon, like a ring-shaped structure, we can add new edges into that graph. We can remove edges into the graph, and through this edit process, I can come up with new structures. I can also keep the same graphs. So a very interesting thing in chemistry is that you can also have two structures that have the same bonding characteristics. So they're isomorphic. But depending on how they're aligned, their energy functions, because of the symmetry or other ways, the energy functions could be very different. So I can keep the graph structure the same, but I can manipulate the geometric positions, and I can also steer the property of a target structure. So the problem for molecule design is that given a database of molecules, can I come up with a new molecular structure that doesn't exist in the database, but has the novel properties? And sometimes it might be that you don't really have a database to start with, because unlike problems in, say, computer vision or natural language processing, where you can get plentiful of data from the web to bootstrap your training, a lot of the scientific problems or applications often don't come with a ton of training data. So in this case, you have to run simulations to create the training data, and that's an expensive process. And to further complicate this, is that this is really the hardness comes from the combinatorial explosion. So I want to show want to give you a sense about the complexity of the problem by just providing a simple equation of the permutations and combinations, that if you were to compose, if you suppose you have a library of 100 different functional groups, and you're trying to compose a new drug molecule by combining 10 of them in different ways. So the number of possible combinations that you can think about is somewhere around 10 to the power 19. You increase that drug molecule size from 10 to 20, and that jumps to 10 to the power 39. Right? So our search space is really huge. And the big role that machine learning plays is that as we start looking for this vast chemical space, how do you rule out, how do you not visit a big part of the machine learning, big part of the chemical space by aggressively pruning out? So I'm going to give you a visual illustration of what that aggressive pruning looks like, and then I'll stop. So think about composing a drug molecule, and I think about building up a drug molecule as no different than playing with some Lego blocks. Think about functional groups, or if you will, someone like me naturally think about subgraphs. I can start with a graph or a molecular structure with just one atom or one node. And then I'm going to perform an action. So let's say I allow only actions in which I can introduce an edge, or I can replicate a structure, I can connect a structure. So given a single node, I can come up with a two node or a single edge graph with essentially think about a molecule with 2 atoms. And then I can keep growing. So I can take the two node or single edge graph, I can add one more edge, and I can come up with another graph with 3 nodes. And depending on how I perform these edits, note how the diversity of this structure. So the top one and the middle one, if you look at just their graph properties, they're identical, they're isomorphic. However, because of the geometric orientations, because one is a straight line, other one is bent at 90 degrees, one is going to be the straight line is going to be much more stable, lower energy, whereas the one bent at 90 degrees is going to be much unstable or much more higher energy. And we can keep growing like this and have the search landscape just blows up as you grow bigger and bigger. So we can add more things, we can replicate. So for example, I can just take this n equals 4 example, and I can replicate it and come up with a much bigger structure. And this is where molecule design, this is why finding new drugs, this is why inventing new materials, new catalysts, this is a hard problem. And a lot of us approach this using reinforcement learning or other generative models. And what I want to stop with by showing that the number of possibilities is staggering. So this is a visualization of a start space where I could start with a simple pentagon, and I could repeat the process that I showed before of adding new edges, replicating, connecting things in different creative ways, and keep building these structures. And as I said before, that my goal is to aggressively prune out this search space. So this is something that I think as a community, this really has taken off in the last 5-6 years. And there's a lot of tools that are needed to do this better. How do you visualize the structure, the state space? Most of the time, we just train a model. We don't even understand what's going on inside. Can you visualize the loss landscape as you're going over this, training this model, and you want to think about this rigorously? So obviously, there's a lot of work to be done. And I want to finish with one more slide that, I started by talking about property prediction, atomistic property prediction. Then I went a little bit into designing new structures. And now if you can do that, what else can you do? And no talk today could be you could finish with that talking about a language model, right? So in the times of ChatGPT, if you are able to predict the property of a language of a atomistic structure, you might also want to talk about in English what that new structure has. And this is something that's really coming up. This is a field that's exploring. And I think learning representations of both chemical or graphs properties, along with joint learning with language, is something that's really taken off in the last 1 to 2 years. And it's a very exciting area of research, but maybe I'll reserve it for a future talk. So I want to finish with thanking all my collaborators, without whom this work wouldn't be possible. And again, thank you, David, for giving this opportunity. I'll take questions.
Thank you so much, Sutanay. Really a fantastic talk. And maybe if I could share my screen, I have a great story, because your talk really piqued my interest in graphs. And I'm not sure if you've heard this story, but do you know who invented the word graph?
I think it goes back like 200 years, right? I think the story of those connecting the river, the town in Germany, right? It was.
No. So that was Euler, who had the 7 bridges of Königsberg, but he didn't use the word graph. The first use of the graph actually related to chemical structures. So a very, very interesting story. And if I pop up on my screen, here's a article in Nature published in 1878, but it was this story here, Chemistry and Algebra, in January 1st of 1878, that a very interesting guy, James Joseph Sylvester, defined the word, and this is the first use in scientific literature of the word graph, to mean a chemicograph, very similar to the structures that you showed. And this is a great article. Maybe if I read the first sentence, it's one of my favorite sentences I've read in scientific literature. It may not be wholly without interest to some of the readers of Nature to be made acquainted with an analogy that has recently forcibly impressed me between branches of human knowledge apparently so dissimilar as modern chemistry and modern algebra. So this was the recognition that there could be connections between a field like chemistry and these graphs. And here's a diagram from a paper of his that shows some of these chemical structures turned into graphs. Again, this is from, I believe, 1878, a paper that he had. Yes. So this guy, James Joseph Sylvester, was the inaugural professor of mathematics at Johns Hopkins University, and he also founded the American Journal of Mathematics. He is credited with the creation of the 2 words that we use, graph, and he also is credited with the first use of the word matrix. So, and others. It's just very, very interesting. So your talk really piqued my interest, coming full circle on what we could do with graphs for these chemical structures.
And it's really fascinating because all the things, I was talking about, I mean, my knowledge of chemistry is still limited to high school levels, right? So, but if you are really good at abstraction, if you really are good at mapping the scientific problems into this mathematical representations, whether it's a graph or I think it's not just the graph, really, you also have to think about the 3D geometry, which makes it more interesting, because then you're also talking about the shape of the graph, right? And now throw in this new threads that are coming up that, okay, how do you explain what's in the graph? How does it smell, right? So that's a whole new tangent that's opening up. So it's a fascinating, I think, time to work on these problems.
So in your research, I noticed that you have done some algorithmic development with graphs. You've used some novel architectures like graph core. You've assembled data sets. What do you think is most needed to continue to make progress in this space?
So it depends, I think, on which perspective you look at. So if you think from the end users in chemistry, the practitioners, I think for them, a big thing need is definitely squeezing the training time. So I would say, there are different audiences. So these are the people in chemistry who have warmed up to machine learning, and they're open to embracing new things, and people who are data scientists. So for them, learning how to train these models, how to bring together different representations, not just graph neural networks, because that's all you can work with, but also integrate with geometry. That's one area. I think the second area is what I talked about, that the chemical space could be vast. It can really blow up. And so just because you can train a model doesn't mean that it will work on a different chemical structure. And so, and I think the risk we have is that for computational chemists who have been working on this, say, for their whole career, they'll say, yeah, this is great. But when it comes to doing real science, they might still go back to their trusted simulations. So I think as a data scientist, our challenge is that how do you establish they improve them and gain their trust that this is working, being able to provide, say, uncertainties where the models are not going to work so well, and use that knowledge further to do more like a self-learning machine where you run simulations on demand. So depending on which objective you talk about, depending on what audience you're talking about, there are quite a few directions. Like I said, because all of this really exploded in the last 5-6 years. So there's a lot of work that needs to be done to even mature this and make this go from cool stuff to something production grade.
Thank you. And if any of our participants have questions, you can either raise your hand in Zoom and I'll call on you. You can turn on your camera and speak, or put your question in the chat. Maybe I can ask one more question. You are running a fantastic group at Pacific Northwest National Lab. What would you tell a student, maybe a graduate student, what type of courses to take to be successful in your research group?
I think, again, it depends on, I suggest that, I think having a strong background in linear algebra, I mean, you should not just learn PyTorch. You should know what's inside PyTorch, how it works. So I think a lot of us have very high mathematical IQs in high school. Linear algebra, calculus, all of that, and then it goes through an exponential decay over undergrad and so on and so forth. So get that shine back. I think that's important because especially for today's students, I think it's important to remember that just learning PyTorch is not going to differentiate you. That's number one. So the second part, I think, is that linear algebra or calculus may not appeal to everybody, and you can stick with PyTorch, but do something that you're very good at, and do it better than others. So if you want to learn PyTorch, then go do something real and publish the code as open source, and so you can stand out. And I think instead of learning too many things, suppose you learn PyTorch, and then just when you're getting good at PyTorch, you say, oh, Google released JAX, I'm going to learn JAX now. So you're going to spend your whole stay in grad school learning hello worlds in 15 languages, and you're never going to be good at doing something real in one of them. So become good at one thing and become so good that nobody asks Michael Jordan how much he scored in geography, right? So nobody, I mean, it's that's what I focus on. Figure out what your interest is. If linear algebra is not your thing, don't go after it. I mean, if you don't like it, there's a reason you don't like it, or you're not good at it. So trying to push or climb that wall is not going to lead you anywhere. So I look for people who are passionate. I look for people who are very good at one thing. I ask them in any interview, what is that one thing you think you're so good than others?
That's really great advice. That passion, that spark, I think means a lot. I noticed in your work you've used the GraphCore architecture, a really novel architecture for doing machine learning training and building models. Are there other architectures that you're also excited by? And does the work that you've done on GraphCore translate to any of the other architectures?
Not so much. I mean, I have been exposed to the Sambanov architecture a little bit. I think they'll represent different design choices. So, for example, Sambanova has a lot of memory per node, whereas GraphCore is they try to emphasize on their lot of memory per chip. So I think, my hypothesis is that Sambanova could be really good for the big graph neural networks. So this is like for the huge social networks. Because if you think about how deep graph library like frameworks there, or Amazon or Facebook, who has really these huge knowledge graphs, how they're training it. I mean, a lot of them are betting on graph partitioning to do this training efficiently. I think some of the reliance on partitioning could be also people skills oriented. I mean, you hire people and some communities are much more focused on partitioning, but if you are able to hold a huge graph in memory, so if you have a few hundred gigabytes or 3 terabytes of memory on a system, you probably can hold a lot of the graph in the memory without having to chop it into 40 gigabyte chunks of a GPU or 80 gigabytes of a GPU. So I think they represent different ends of the hardware design spectrum. And I have not really done hands-on work on Sambanova. I mean, this is my hypothesis. So I think, I think about Sambanova on one side, GraphCore on the other side, and NVIDIA's sort of in the middle. But that's a personal observation.
Thank you. Are there any questions from our audience here? I think there is one from Tara Narahara. In the second part, you showed examples that generate new graph patterns with certain performance characteristics. Do you recommend any papers to learn more about generative applications?
I mean, there is a lot of papers on the topic. So if you look for, there are papers coming from variational autoencoders. So if you look for JTVAE from MIT, they have developed a lot of models on graph-based representations. Yuri Leskovic's group also had, if you look for GCPN, Graph Convolutional Policy Network, if you like reinforcement learning, that's again another option to explore. So there is quite a bit of, if you just do a Google Scholar search, you'll find some things. But you'll find something around, reinforcement learning, and definitely with variational autoencoders. And I'm not getting into language models here, generative.
Thank you. Any other questions from the audience?
If I can add one more thing to that answer.
Sure.
So there a very recent focus in the community is that for generative modeling is you want to give an English description of what you want in a molecule, and you want a generative model to create the graph structure. So this is a very nascent thread. And so if you look for something called MolGPT, that's a good starting point.
Thank you. That's very helpful. So I don't see any other questions. So Sutanay, I really want to thank you for this great talk. For those attending here, it will be available on our YouTube channel in about 24 hours after it gets processed. And I hope everyone here really enjoyed this talk as much as I did. So again, Sutanay, thank you again for attending and presenting our NJIT Data Science Seminar.
Thank you, David. Really appreciate the opportunity. Bye.
Take care. Bye-bye. Take care, everyone.